Hello, everybody. This is Dr. Ekstrom, and this is the second of seven video lectures for our second workshop. This one, we're going to look at pure substances and mixtures, and this time it's going to be more from the macroscopic level, the observable properties level. And so I think a lot of this will be familiar to you and your students, but I want to put this in its proper context with the rest of the content here for this workshop. A pure substance is one that always has the same composition. Now, a substance can be either an element or a compound. Doesn't matter if it's molecular or ionic. Uh, Examples: pure water, carbon dioxide, hydrogen, gold. Uh, with a pure substance, the elemental and or molecular composition is going to be uniform throughout. Now, this contrasts with mixtures, which have variable compositions depending on, there are different types of mixtures. They have variable compositions, meaning they may contain different compounds or contain different mixtures or substances. There, of course, are plenty of examples of mixture in nature and man-made mixtures: wood, wine, and coffee, for example. Probably the key quality, as far from a definition standpoint about mixtures, is that they can be separated into pure substances. Sometimes easily, sometimes not so easily, but that is the key. And we'll talk about a couple of different ways in which chemists do that later on here in the video. Now, there are two types of mixtures. We can classify them as homogeneous or heterogeneous. Now, homogeneous mixtures, the composition is consistent throughout the sample. So basically what that means is that you visibly cannot tell that there are two substances mixed together. We also call this a solution. You could sample or take a sample from a homogeneous mixture, and it wouldn't matter where you take it from, that you would end up with the same composition. The atmosphere around us is a gas phase solution, a homogeneous mixture. In the upper right-hand corner, there's a picture of brass. Brass is a solid state solution of copper and zinc, completely thoroughly and consistently blended together. And then, of course, probably the most common homogeneous mixtures that we work with are liquid solutions, or solids, either liquids mixed together or solids dissolved into liquids. For example, table salt stirred into water. The salt visibly appears to disappear into the solution, and you cannot visibly tell that you have water and table salt there together. Now, a heterogeneous mixture, on the other hand, consists of visibly distinguishable parts. So the metamorphic rock in the upper right-hand picture here on the screen, you can tell where you have different minerals in different places in the sample. If you were to take sand and stir that into water, that's a homogeneous mixture. The sand is still visibly present and actually separates itself out from the water. So these are called heterogeneous. Of course, this kind of topic is easy to quiz students about. So, remembering back to the first workshop when we had quiz-based games, you could ask students questions like, which of the following is a homogeneous mixture? Going through the choices, of course, pure water is a pure substance, so that's not a mixture. Gasoline is a liquid where several different compounds are blended together. We have a jar of jelly beans. Now those, thinking of the colors as different substances, that's really more of a heterogeneous mixture. Soil is another example of a heterogeneous mixture. You've got dirt, minerals, and rocks, and all these things mixed together that don't completely blend. And then finally, copper metal is another pure substance. So our answer here would be gasoline as far as a homogeneous mixture goes. There's anywhere from 6 to 20 compounds mixed together in gasoline, depending on the particular blend that a refinery generates. Now, as I said earlier, The key attribute that defines a mixture is that it can be separated into its individual substances, depending on what the properties of those components are. And so we can separate compounds based on them having different boiling points. So if at least one of the compounds in the mixture is a liquid, we can use a process called distillation. Um, if we have a heterogeneous mixture, particularly if one's a liquid, one's a solid, we can use filtration. There is a more chemically advanced technique called chromatography, which can actually be used to separate compounds in a homogeneous mixture based on how strongly they adhere to a surface. We call a chromatography column. And then finally, volatility, that's kind of a variation on distillation. Volatility requires difference in boiling points. If we have at least one liquid in the mixture, we can just simply use evaporation to separate the components out. I would like to talk about a couple of these. And the first process is called distillation. This is very commonly done in chemistry. And what we do is we take a mixture that has at least one liquid, and we boil that liquid and direct the resulting gas into a condenser. So here what we have in the pictured here is a sample of salt water. We take the salt water, put it in a round bottom flask, and boil the water. The water of course, evaporates and then finds its way into this central tube. This is called a condenser. It's a jacketed tube. The steam goes into the central channel, but then surrounding it, we pipe in cold water. And so that lowers the temperature of the steam enough so it condenses back into liquid water, and then this is collected into a flask at the end of the apparatus. And so in the end, if we do this to completion, we can completely separate the salt and the water. The salt is a solid with a very high boiling point. It will not leave the flask, whereas the water can be completely distilled over. So this is a physical method because we're doing nothing to the composition. We started with a homogeneous mixture that contains sodium chloride and water. And then after the distillation, we still have those same two compounds, but they are now physically separated. Lastly, I'd like to talk about filtration. You may have your students do this in some experiments. The picture on the right shows a technique called gravity filtration, which is probably what you've done in your classrooms. We do that a lot at the college level. Basically, what we do is we have a heterogeneous mixture. We have a solid mixed with a liquid, and sometimes this results after we've done a chemical reaction that generates a solid that is not soluble in water. We pour it through a funnel that has a piece of filter paper. And the filter paper has pores that are small enough to let the water through, but it traps the solid particles. And then we call this gravity filtration. We let gravity take over, and the liquid slowly drains through the funnel. You can speed up this process somewhat if you use a vacuum pump to actively, or we say dynamically, pull the liquid through the filter. So in the picture on the left, you show how this is set up. The funnel up here in the upper left is we often use called a Buchner funnel, and then there's a flat piece of filter paper that we put in the bottom here. We pour in our mixture, and then with the vacuum pump actively pulling down, so it's pulling a vacuum, so pulling the air out of the filtration flask helps to actually bring the water down through the funnel. So that's it for this lecture. We'll continue on in lecture 3. Thank you.